This video describes a procedure that allows the descent portion of a visual traffic pattern to be accomplished with only one pitch attitude and one power change. The procedure applies the flap and gear rules that were developed in a previous YouTube video. The flap and gear rules were applied to both instrument and visual profiles. The instrument procedures were covered in the Instrument Approaches, Props and Jets YouTube video. This video applies the visual rules, where after the final descent is initiated with gear extension, flaps are extended to slow down during the final descent. This procedure applies to any airplane. It allows descent from the downwind leg to the flare point with only one pitch attitude change and one power reduction, avoiding unnecessary changes. Pilot workload is reduced, and passenger confidence and comfort is enhanced. This technique applies flaps correctly, extending them to slow down while maintaining approximately the same flight path angle. When extending flaps while holding pitch attitude and power constant, airspeed will decrease and stabilize after each flap extension. Flight path angle changes will be minimal after a small bump in the flight path while airspeed is changing. In this example, the airplane is on downwind leg at 120 knots with flaps 5 and gear up. Opposite the desired touchdown point, gear down and flaps 15 are selected, and the final pitch attitude and power are set. Maintaining the pitch attitude at 0.5 degrees and the manifold pressure at 16 inches. Flaps 20 is set at the 45-degree point as the turn to base leg is begun. Flaps 30 is set at the beginning of the turn to final approach. After completing the turn, the airplane is now in the full landing configuration and the correct final approach pitch attitude and power setting. So the airspeed and flight path will stabilize at their desired values, 90 knots and a 3-degree descent angle. Although we are referring to the pitch attitude in degrees, it is important to note that this visual pattern should be controlled using outside attitude references rather than numbers on the attitude indicator. One example of a visual reference is the distance from the horizon to the top of the instrument panel directly in front of the pilot. Why did we initiate the final descent by extending landing gear and flaps together? Beginning descent on downwind leg abeam the desired touchdown point with landing gear only may result in a premature descent with a final approach that is too short and too low. Combining flap extension with gear extension delays the initial descent, allowing a longer stabilized final approach. Also, why did we extend flaps at the beginning of turns? Banking steepens the flight path and increases airspeed when pitch attitude and power are constant. Extending flaps at the beginning of turns slows the airspeed and allows the flap-induced bumps to compensate for the steeper descent angle caused by banking, thereby producing the smoothest overall flight path. In this view of the example pattern, we see that after initiating the final descent with gear down and flaps 15, and setting the final approach pitch attitude and power setting, the airspeed slows from 120 knots to 100 knots. Then after setting flaps 20 and turning onto base leg, the airspeed slows to 93 knots. After setting flaps 30 and completing the turn onto final approach, the airspeed stabilizes at 90 knots and the angle of descent stabilizes at 3 degrees. After verifying that all speeds meet minimum requirements, multiple patterns are flown in a no-wind condition until fine-tuning the pattern size results in a touchdown occurring at the desired point after an adequately long stabilized final approach. Now let's watch the computer simulation fly this example pattern. For comparison, this first pattern is flown with flaps applied after the turns rather than at the beginning of the turns. We are now on downwind leg at 120 knots and flaps 5 with a pitch attitude of 2.8 degrees and a power setting of 16 inches of manifold pressure. Opposite our touchdown point, we select gear down and flaps 15, while setting the final approach pitch attitude of 0.5 degrees and the final approach power setting of 16 inches of manifold pressure. After completing the turn to base leg, we select flaps 20. On final, flaps 30 is selected and the airspeed slows to 90 knots. In the profile view, note the irregularities in the vertical flight path. In this next video, we will look at a close-up of the vertical flight path in a turn when flaps are applied after the turn versus at the beginning of the turn. In this first example, flaps are applied at the completion of the turn. Next, flaps will be applied at the beginning of the turn. Note the straighter flight path when flaps are applied at the start of the turn. At this point, we'll again fly the pattern applying flaps at the beginning of the turns and compare the results with the previous pattern flown with flaps applied at the completion of the turns. Gear down, flaps 15, and set the final approach pitch attitude and power. Maintaining the pitch attitude and power constant, set flaps 20 and begin the turn to base leg. Next, set flaps 30 and begin the turn to final approach. On final, the airspeed slows to 90 knots and the flight path angle stabilizes at 3 degrees. Again, we can see how more uniform the flight path is when flaps are applied at the beginning of the turns. In summary, this demonstration illustrates a light airplane traffic pattern where a constant pitch attitude and power setting are maintained throughout the descent to the runway. The procedure applies the previously described flap and gear principles, since gear extension initiates the descent from pattern altitude and flaps are used to slow down. Because banking with a constant pitch attitude causes an increased descent rate and increase in airspeed, it is important to extend flaps at the beginning of turns, since flap effects compensate for banking effects. The result is a smoother flight path and airspeed change, as shown by the second example compared to the first. Traffic pattern configuration options vary with the number of flap settings and whether the airplane has fixed or retractable landing gear. This graphic illustrates some of the possible options. In any case, the general rules apply. Initiate descent with gear, if retractable, and set the final approach pitch attitude and power setting. Select flaps at the beginning of turns. The constant pitch and power visual approach can also be applied to base leg or straight-in approaches, as shown in this jet approach. The airplane is initially at 1,500 feet and 160 knots with flaps 15. The descent is begun by selecting gear down and flaps 20 and setting pitch and power to 2.8 degrees and 1.09 EPR. Maintaining the pitch, attitude, and power constant, flaps 25 is selected at 1,200 feet. At 900 feet, flaps 30 is selected and the airspeed slows to 140 knots. By 500 feet, the airspeed and flight path have stabilized at 140 knots and 3 degrees. Today, this type of visual approach applies more to smaller prop airplanes rather than jets. Airline jet transports universally fly a stabilized final approach in full landing configuration in all weather conditions, as described in the Instrument Approaches Props and Jets YouTube video. Now that we understand how the constant pitch and power traffic pattern works, let's use a flight simulator to illustrate the steps in setting up the pattern for a typical light twin. This airplane has retractable gear and 2 flap settings, approach and full. The first step is to determine the final approach pitch attitude and power setting. Start by choosing the final approach airspeed and rate of descent. For this airplane, final approach speed is 92 knots, and the rate of descent for a 3-degree angle is just under 500 feet per minute. Rate of descent for a 3-degree angle can be found by multiplying the approach speed in knots by 5.3. We have now extended the landing gear and set full flaps, and have reduced power to slow down. As the airspeed approaches 92 knots, we adjust pitch and power until the airplane stabilizes at 92 knots and 500 feet per minute. We now note that the final approach pitch attitude and power setting is 0 degrees and 15 inches of manifold pressure. Now, with gear still extended, we set approach flaps and hold the pitch attitude at 0 degrees and the power setting at 15 inches. Note that the airspeed stabilizes at 107 knots, which we verify is a safe airspeed at this flap setting. Now, we will repeat the prior step with flaps up, again holding the pitch attitude at 0 degrees and the power set at 15 inches. We see the initial descent condition of 120 knots and 600 feet per minute with gear down and flaps up. This is a safe airspeed with flaps up. We will level off at 1,000 feet to determine the downwind leg settings. Leveling off, we raise the gear and watch the airspeed. If the speed stabilizes at 120 knots or greater, then 15 inches of manifold pressure would be our downwind leg power setting. This was the case for the previous jet visual approach, which used the same power setting for the downwind leg and the final descent. In this case, we see that the airspeed drops below 120 knots, so we will select 120 knots as our downwind leg airspeed and must add power in order to determine the manifold pressure that will maintain it. We now see that our downwind leg condition of 120 knots in level flight requires a pitch attitude of +2 degrees and a power setting of 17 inches. A faster downwind leg airspeed could have been selected if desired. We will now test the entire configuration sequence, in order, before trying it in the traffic pattern. Starting in level flight at 120 knots with gear and flaps up and pitch and power set to +2 degrees and 17 inches, we select gear down and set pitch and power to 0 degrees and 15 inches. We note that the airspeed remains at 120 knots and the vertical speed stabilizes at 600 feet per minute. Maintaining the same pitch attitude and power, we select approach flaps and note the airspeed stabilizes at 107 knots. Finally, still maintaining the same pitch attitude and power, we select full flaps and watch the airspeed and vertical speed stabilize at 92 knots and 500 feet per minute. We are now ready to apply this sequence to an actual traffic pattern. We are now in level flight on downwind leg. The small window shows a view of the runway off the left wing. Opposite our touchdown point, gear down is selected and pitch attitude is set to 0 degrees and the manifold pressure is set to 15 inches, the final approach values. Starting the turn to base leg, approach flaps are selected. On base leg, the airspeed has slowed to 107 knots, and the small window now shows the left front view. Full flaps are selected as we begin the turn to final approach. Rolling out on final approach, maintaining the same 0 degrees pitch attitude and 15 inches of manifold pressure, the airspeed slows to 92 knots. The stabilized approach continues until flare height, and the landing is completed. The purpose of the traffic pattern is to place the aircraft on final approach at the desired airspeed and descent angle in the full landing configuration at a sufficiently high altitude. This altitude allows time for any required small adjustments. The minimum final approach altitude in visual conditions is commonly considered to be 300 feet for light airplanes and 500 feet for jets. Fine-tuning the pattern requires in-flight experimenting in no-wind conditions. If the final approach altitude meets the basic criteria outlined above, no further changes are required. If not, consider the following changes to make the final approach begin at a sufficiently higher altitude. We can increase the pattern altitude. This is common for large airplanes, but is not always practical for light airplanes. Or we can increase the downwind leg airspeed. This method has a small effect only and may be undesirable. Another option is to increase the descent power setting. This is okay for small changes, but it changes the final approach speed and descent angle. The best choice is to begin the descent later. This is the most practical solution if a higher pattern altitude is not desirable. After we have fine-tuned the constant pitch and power traffic pattern in no wind conditions, let's consider the effect of a headwind on final approach. If we fly the no-wind pattern in this case, we will land short. This can be avoided by increasing the descent power setting, which reduces the average rate of descent for the entire descending portion of the traffic pattern. Other than this increased power setting, all other parts of the traffic pattern procedure remain the same. This picture shows a no-wind pattern compared to a pattern with a 20-knot headwind. Let's watch the computer simulation fly these patterns. This is a repeat of an earlier computer simulation with no wind. Descent is begun by selecting gear down and flaps 15 and setting the final approach condition of 0.5 degrees pitch attitude and 16 inches of manifold pressure. Maintaining the same pitch attitude and power, flaps 20 is selected at the beginning of the turn to base leg. Turning final, flaps 30 is selected, airspeed slows to 90 knots, and the flight path stabilizes at 3 degrees. At this point, let's repeat the pattern with a 20-knot headwind, making only one change. The descent power setting will now be 18 inches of manifold pressure rather than 16. Notice the reduced descent angle on downwind with the tailwind. The headwind on final will produce a steeper approach angle that compensates for this effect. This procedure results in a slightly increased airspeed on final approach, which is not a bad thing in a strong headwind. Both touchdowns occur at approximately the same point. Additional computer simulations show that all headwind and crosswind directions, except 90-degree crosswind from the traffic pattern side, require increased descent power settings compared to the no-wind value. In summary, to adjust for headwind components in the traffic pattern, fly the same pattern size, regardless of wind speed. Increase the descent power setting as the wind speed increases. Fly the usual no-wind, constant pitch attitude and constant power approach. And ignore altitude. Turn onto each leg at the same place regardless of wind. Even though your altitude will be higher at any given point compared to the no-wind case, the extra altitude will be lost when flying into the wind on final approach. Summarizing wind corrections. When a wind is present, use the same procedures and pattern size as the no-wind case, except you must adjust the initial descent power setting for the wind. In other words, increase the initial descent power setting when a headwind on final is present. As discussed previously, most other wind directions will also require a higher descent power setting compared to the no-wind value. Experimentally finding the correct power adjustments for various winds allows rules of thumb to be created that will make precision patterns possible in most any wind condition. Finally, let's fly the flight simulation traffic pattern again in order to consider some practical considerations. As we begin our descent from pattern altitude, we believe that our downwind leg is the correct distance from the runway. However, we know that this distance and other variables, such as the point to turn onto base leg and the actual wind, can add considerable errors to our normal pattern procedure. Therefore, we must be prepared to make in-flight adjustments. The power fixed, power variable rule, taught during Air Force basic flight training, outlines the procedure for making these adjustments. After turning onto base leg, we can get a sense of being either high or low. Since we have no precise visual flight path, we can control only one variable precisely, in this case pitch attitude. Therefore, this is a power fixed situation, and if we are high or low, an adjustment in the fixed power setting is appropriate. Now, as we turn on to final approach, we begin to sense precise visual flight path information, and now have the ability to correct both flight path and airspeed precisely, which is a power variable situation. Therefore, for the remainder of the final approach, we will control flight path with pitch attitude and airspeed with power. We are now aiming for the threshold crossing height with pitch, while coordinating power adjustments to maintain the airspeed constant. Let's summarize the power fixed, power variable procedure. Until getting closer to the runway, there is no precise visual flight path, so the only variables that can be controlled precisely are either pitch attitude or airspeed. In this constant pitch attitude traffic pattern procedure, we choose pitch attitude. Since only one variable is now controlled precisely, this is a fixed power situation, where pitch attitude is maintained with pitch control and power remains constant. As shown in the pitch and power control YouTube video, we note that an occasional change in power does not change a power fixed condition into a power variable condition. It simply is a slight adjustment in the fixed power setting. The power variable rule does not take effect until a precise visual flight path is available. When it is available, then minute and continuous adjustments are used to control flight path with pitch attitude and airspeed with power. One final comment. Perfecting the constant pitch attitude and power traffic pattern procedure will make your patterns more precise and considerably reduce your workload, as well as reduce the anxiety of your passengers. Related videos mentioned earlier can be found at youtube.com/user/cchpub.